Now, this motional EMF result is extremely important, even of its own right, because it gives us the fundamental underlying theory of electrical power generation. It shows us how we can get the same type of charge separation that we find in batteries from chemical energy, but produce that instead by moving wires through fixed magnetic fields. So this is important in and of its own right. It has another very profound implication, though, for the underlying laws of physics, for the structure of Maxwell's equations. But that requires us to do a little additional thinking. If you think about what we've done and proved so far, we actually haven't used anything exotic or assumed anything exotic in Maxwell's equations. All that we've really done is said, well, from the Lorentz force law, when we have conductors moving through magnetic fields, there are these additional magnetic forces, and those forces have various implications for us that imply then we can drive charges around a circuit. But we didn't assume that there was anything really exotic going on in terms of the value of the electric field or any, strange, mysterious forces going on. It was all just our traditional, we calculate voltages by integrating up electric fields. In fact, we assumed our normal circuit type analysis. So in fact, we assumed, and correctly so, by the way, that only these terms here were active in Maxwell's equations. We haven't really touched on this issue of a truly changing magnetic field. So let's go and look at that in a little more depth here. And what can help clarify all of this for us is the following thought experiment that helps us clarify those distinctions. So here's a thought experiment for us to analyze. So let's imagine that I have some magnet, right? So I'm going to have some bar magnet or something like this. And that bar magnet has some magnetic field lines associated with it, coming out, say, from this end of my magnet. So the field lines, as you can see, are getting further and further apart as I get away from the end of my bar magnet. That simply means that the magnetic field is getting weaker and weaker. And then what I'm going to do is I'm going to take a wire loop here, right, like so. And I guess I'll break my wire here. Here there's a break in the wire because it's going sort of behind my bar magnet. Actually, let me draw that a little more clearly for you guys here. Okay, so here's going to be my magnetic field lines, and say maybe my loop looks something like this, right, where it's gone to the point where here's some more magnetic field lines coming out of the other side here of my loop, like so. Now I'm going to break my loop, and I'm going to wire it up maybe to a light bulb. I'm going to try to draw a better light bulb for you guys here. So here's a little light bulb, and I'm going to wire it up to this loop, and then here's my light bulb. And then what happens is if I take my loop here and I jiggle my loop here, and I'm going to jiggle it here back and forth, back and forth, back and forth. And as I do that, right, because the magnetic field is changing its magnitude in the plane of the loop, as I jiggle the loop back and forth, the flux through that loop is changing. And then this very general result that I have, notice when we proved that, I didn't assume anything particular about how the wire was moving or how the magnetic field was oriented. It was a fully general geometric result. So it's definitely going to hold in this case that as I'm moving my wire through my fixed magnetic field, I'm going to be generating these charge separations and generating some effective EMF. And as a result, as I do that, my light bulb here is going to light up as I move this wire here back and forth, back and forth, back and forth. Okay. So that much, I think, is clear from our analysis so far. But now we come to the point as to, well, how much do we really believe in relativity? Because I could do this experiment just slightly differently. I could have the same apparatus. So let's call this portion here where I'm moving my loop back and forth, let's call that experiment 1. In experiment 2, I'm going to hold my loop fixed. And in experiment 2, what I'm going to be moving back and forth is actually the magnet. And I'm going to move that one back and forth. And when I do that, we are left with an interesting dilemma. There are two ways of looking at this, two possibilities as to what will happen when I move number 2 back and forth. Here's the first level of analysis. From our E&M knowledge so far, and I should emphasize so far, we would conclude the following. Okay, I'm jiggling my magnet back and forth. That's nice. But notice, as I'm jiggling it back and forth, right? There are certainly some magnetic fields involved here, and the magnetic fields are changing in time. That's certainly true. But from what we know so far, right, there's no reason to expect that there's any electric field in this situation whatsoever. Right? I'm just moving a magnet around. So there's no reason to expect there to be any electric field associated with that. And if there's no electric field, then something very interesting comes out of the Lorentz force law. The Lorentz force law states that the forces on any charges come through a formula like so. Now, in the case where the wire is moving through a magnetic field, then we know this V cross B term puts some forces on these charges, and as we saw, that results in polarization and driving charges around a circuit and the EMF and that whole story. But we're not now moving the wire. The wire is not moving. Because of that, there are no magnetic forces on the charges in my wire. The only way there can be any force that would tend to drive any charges around my wire would be if there were some electric field in the situation. But from our current knowledge of Maxwell's equations, right, there doesn't seem to be any reason to believe that there would be an electric field. I just have a magnet. I don't have any free charges sitting around to create a magnetic field. That is, of course, unless we start to actually believe that there is a mathematical term like this in Maxwell's equations. If there were, then it's possible that a changing magnetic flux would generate an electric field through this type of a connection. But right now, we are just positing, or have been, that these two equations are just zero. So one way of looking at it is to say, let's just go with the equations that we know, and in those equations, there's no reason to expect any electric field. And because the wires aren't moving, there are no magnetic forces. So all I have is, a magnet here jiggling around and a whole set of charges in my wires that are not feeling any electric fields, and there's no reason then for them to move, right? They have zero velocity, and so the magnetic field's nice, but the force is V cross B, and if V is zero, there is no magnetic force. So from our knowledge of electromagnetic theory so far, we would say there's no force on the carriers, Q, and the bulb doesn't light. Put a question mark on that because the second possibility should give us some pause, right? Let's use our common sense here a little bit, right? If I'm jiggling the wire back and forth, that makes the light bulb light. If I hold the wire fixed and just jiggle the magnet back and forth, how can that be really that much different? Do we expect that's going to be any different, right? Do we believe in relativity? Does it matter which one's moving relative to the other? Should the bulb light or should it not light? So the second thing to expect is, well, from relativity or common sense even, it should light. So if it does, and the physical situation is actually going to do one or the other of these two things, right? Either the bulb lights up or it doesn't. you can go ahead and actually you have to do this experiment to determine which of the two possibilities holds. And the result is that, in fact, the bulb does light when you jiggle the magnet back and forth, which is kind of what you would expect. But the beauty of that then is that if that bulb does light by jiggling that magnet back and forth, well, we know then that there is some force driving the charge carriers through that circuit. And that force can't be a magnetic force because there's no velocity associated with this wire moving. There must be some electric fields that are generated. There are no excess charges anywhere that are creating that electric field. It must be due to the changes in the magnetic field because of the fact that we are moving the magnet. That is therefore direct evidence that there must be some term in Maxwell's equations along these lines here. And moreover, we know from how bright that light bulb lights up that the form of the term is that this effective EMF, this integral of E dot dl, must come out equal to what it does when we're jiggling the wire. And in the wire case, that gives us the motional EMF, and that's related directly to the time derivative of the magnetic flux. So we know quite a bit about this term, and we will take up those considerations later on in the course.